traveling salesman, and heuristics. At the conclusion of this, you'll be able to determine if an algorithm runs in a reasonable amount of time. You should be able to develop a heuristic to solve a problem, to distinguish between decision problems and optimization problems, and then explain the existence of undecidable problems. What is the difference between a reasonable and an unreasonable time algorithm? And not just polynomial or exponential. What makes one unreasonable? Well, reasonable algorithms grow at a polynomial rate or slower. Essentially, they can be computed. You can run through them in a reasonable amount of time. Unreasonable algorithms grow exponentially. They grow so fast that the amount of time to run them would just be way too long. The time to solve an unreasonable algorithm grows very quickly, even for relatively small problems. Now, the activity we're going to do is based a little bit on what we've already done in this unit. The prompt here was a good reminder of what we learned last time. Unreasonable time algorithms just don't make sense to run. Today, we're going to be thinking more about what happens when we reach the limits of algorithms and how sometimes we can make compromises. In life, we can't always have everything, so we compromise. We have to do that sometimes with solving problems. Here we're going to have the traveling salesman. You should have your journal or notebook and pencil and paper. Okay? Now, here, draw 4 little houses. How many different paths can you find to visit all of your friends' houses? You must start and end at your own house. That's the blue one. And you can only visit each of the other houses once. Take a moment. Draw out some paths. Well, here are some different paths you might take. You might simply go around in a circle. You could go the other way. You could do a few zigzaggy diagonals. Well, these are all visiting your friends' houses. But what do you need to know to determine the best path? Distance. If we know the distance between each house, we can make a better decision about which path to take. In this example, the first option is the shortest, so that's the path that we would choose. Notice you go around 1, 1, 1, 1, 4. Okay. This distance is 1, 2, 3, 4, 5, 6. And I don't know why this one says 4 because that's also a 6. 2, 4, and 6. Okay. Now, what if we had a lot more places to visit? How would you determine the best path? How? All of a sudden, this became hard, right? This is known as the traveling salesman problem. For every new place to visit, the number of options for possible paths increases factorially. You all remember what factorial is? Okay. A factorial. 1 factorial is 1. 2 factorial is 2. 3 factorial is 6. 4 factorial is 24. Yes. Remember that 5 factorial is 5 times 4 times 3 times 2 times 1. It's how many times that number of items can be arranged. So notice that things grow rather quickly, okay? When you get up to 8, you now have 40,320 permutations of 8 items taken 8 at a time. Okay, so factorial grows quickly. It's something that's important to know. And notice even at 10, we're up to over 3 million number of steps to check for the best path. That's a lot. Now, factorial fun, multiply all whole numbers from the given number down to 1. So 4 houses would be 4 times 3 times 2 times 1, or 24. 7 times 6 times 5 times 4 times 3 times 2 times 1 is 5,040. Wow, that was fast to get a very large number. Now, problems. Any task that may or may not be solved with an algorithm is a problem. Sorting a list is a problem. Sorting the list 2317 is an instance of that problem. So there's problems, and then there are specific instances. Now, we have two different kinds of problems. We have decision problems. Is there a path? Can I get from point A to point B? And optimization problems. What is the shortest path? Once we determine there is a path, now there are multiple paths. Which one is shortest? The traveling salesman problem can be solved with an algorithm which checks each possible solution. But, and it's a big but, it would take massive amounts of computing power to compare every single option, especially as the number of homes to visit, otherwise known as nodes, increases. Therefore, it would take an unreasonable amount of time for the solution to be calculated for most instances of the problem. So it could be done, but it would be an unreasonable amount of time. Welcome to Heuristics. This is where you're going to provide a good enough solution to a problem when an actual solution is impractical or impossible. Okay? Good enough. A heuristics. Good enough solutions. Do this. Go to level 2, go to unit 6, lesson 4, level 2 on Code Studio, and try to find the best path to visit all the nodes. Write down a plan or heuristic for choosing a good path. Note your heuristic may not always find the best path, but it should be close enough. So go ahead and try. Pause the video and do that. Take about 4 or 5 minutes. All right, now go on to level 3 on Code Studio. Test your heuristic on 3 different levels. Write down the distance for the path your heuristic finds. Try to find the best version, not using the heuristic, just brute force. Can you find a better path? Is your heuristic, on average, pretty good? Should you update it? Pause the video and work on this level for another 4, 5, 6 minutes, okay? Now, how did you create your heuristic? Did you change your heuristic after you tested it out? Did you say, I don't think it was good enough? I'm going to share this out in class, okay? We're going to share it out, figure out, as a class, did you have to change it or not? And explain what your heuristic is. All right? Now, a sample heuristic. At each node, travel to the next closest node. That's a heuristic. Is it good enough? Try it out. The traveling salesman is an optimization problem. We are attempting to find the best path. Not is there a path, just the best path. It is also unreasonable because there is not an algorithm that can solve the problem in a reasonable amount of time. We need to use a heuristic to come up with a solution that is good enough for most instances. Now, again, problems, any task that may or may not be solved with an algorithm. Sorting a list is a problem. Sorting a specific list is an instance of that problem. We have decision problems. Is there a path? We have the optimization problems. What is the shortest path? Sometimes optimization problems require heuristics because they're unreasonable amounts of time to really find the best. But what about this crazy thing? An undecidable problem. Will this code even work? Let's watch this video. And if you're watching the video now because you missed class, when you're done here, go and watch the halting problem. You don't have to. This is to let you know what an undecidable problem is. You're not going to be tested on the halting problem. Takeaways. Well, there are some problems we've proven that no computer will ever be able to solve. The halting problem is a very famous example, and in general, we call these problems undecidable. Why is a heuristic acceptable when it doesn't always produce the best results? Because it's a compromise. And in life, oftentimes we make compromises. We want to find a good enough solution when we can't possibly spend enough time to find the best. A heuristic provides a good enough solution to a problem when an actual solution is impractical or impossible. Undecidable problem is a problem for which no algorithm can be constructed that is always capable of providing a correct yes or no answer. Last up for this unit will be Lesson 5, Parallel and Distributed Processing. Have a wonderful day.